let's wait until the end of the talk to see if that's warranted. This is joint work that I've done with what was just by accidental hiring the modest combinatorics group that we have at Marshall University. It was stuff that we did maybe about 3 years ago, and it just took a while for us to finish it and get it submitted. And I'm looking at the audience, and I don't see Charlie here. I expected as much because I'm competing against a talk on location arrays. I figured it was a foregone conclusion. So I wanted him to be here, so he will be in the lower left-hand corner of every slide. So that way he can be in both locations at once. All right, so the notion of erasure combinatorial batch codes kind of was distilled over time from a data retrieval problem that is best illustrated with an example. So suppose you're Netflix. Netflix is an online service for distributing streaming media, whether it be TV shows or movies. And as Netflix, in order for you to provide your service, there's going to be a collection of movies that you would like to have available to stream to different customers. You have a certain number of servers that you can store your movies on for doing the streaming. Each of your servers can have some capacity for being able to deliver some number of movies simultaneously, and you'd also like to be able to guarantee some amount of service. Now, if you have 1,000, let's say you have 1 million customers, you don't necessarily want to be able to stream 1 million movies at a time because, well, that's a little unreasonable to expect. Everyone would want a movie all at the same time. So you have some smaller threshold that you just want to make sure that if you have a request for that many movies that you can deliver it. And so the two natural questions, first off, is there a storage configuration on your servers with these restraints that actually can be achieved? And then if you can achieve it, what is the minimum amount of storage you would need in order to do it? And so let's look at a small example. Suppose you have 4 servers and you're going to store 5 movies on those servers, and you'd like to be able to satisfy a demand of delivering 2 movies simultaneously. And we'll also assume that each server can only deliver 1 movie at a time for the time being. So here are our 5 movies: Harry Potter, the Titanic, Happy Gilmore, the Avengers, and of course We Are Marshall, which is my home institution. Now, one simple solution is that you can just store every movie on every server. And so if you wanted to download the first 2 movies, you can dedicate 2 servers to do that. If you wanted to download the 3rd and 5th movies, you could also find 2 servers to do it early. You can pick any 2 servers to deliver any 2 movies that you want. And so the answer of existence is yes, in this particular case. But of course, you don't need to store as many copies of your items on these servers. You could just do fine by storing everything on 2 servers. But you can do better because you're not utilizing the fact that you have 2 other servers at your disposal. So one thing you have to notice is that every movie needs to be stored on a server, so you know you at least have to have 1 copy of each movie somewhere. So if you started with a configuration like this, you would be able to retrieve any 2 movies simultaneously except for the 1st and the 5th one. So you need to have an extra copy of one of those movies somewhere without loss. I'll just go ahead and put one there on server 2. But of course, if you increase what you want your demand satisfaction to be, let's say you want to go from 2 movies to 3 movies, well, you have a similar situation that your 1st, 2nd, and 5th movie are only available on 2 servers, so you need to have another copy of one of your movies somewhere. If you want to be able to download all 4 of them simultaneously, we're going to need another copy of one of the movies somewhere. You can verify that you can find an assignment for any 4 of those movies on those 4 servers, given this particular storage configuration. So really what we're looking at here is what is technically called a combinatorial batch code. And this is defined in a paper by Patterson, Stinson, and Way from 2009. It's a combinatorial version of a problem that was studied in 2004 by Ishai and 3 other mathematicians whose names escape me. But this is distilling it just to a design theoretic setting. So you have a set of elements, which are like the movies, and you want to find a multifamily of subsets of your elements, which are the servers, so that if you were to take any k subset of your items, then you can find subsets of each of your subsets in the family, so that Each of them is of size at most t, t being the capacity of each server, and the union of those sets will give you the set of items that you're demanding. So essentially, it's just codifying what we saw in the last example. Now, to see that in action, I'm going to only focus on t equal 1 for this talk. And notationally, we have 4 parameters here. We have n being the number of items, m being the number of servers, k being the batch size or the demand size, and t being the capacity of your servers. We'll see enough examples to where hopefully the alphabet soup won't confuse you. But with t being 1, that means that every server is only going to be able to deliver 1 movie, and so I'm just going to ignore that last parameter for this talk. Okay, so going back to our original example, this is a combinatorial batch code with 5 items, 4 servers, and a demand capacity of 3. My family of sets will be these 4 guys here, 1, 5, 2, 5, 3, 5, and 4. And inside each of them, I can find a subset. For example, if I wanted to pull movies 2, 4, and 5, then I can find subsets in each of those 4 sets that, when I think their union, give me 5, 2, and 4. That's what I'm looking for. Now, this is, by most accounts, the inconvenient way to look at a solution to this. Usually, we like to look at this from the dual aspect. And so instead of thinking of the rows or the servers as our sets, we often think of the columns as our sets. And so the dual definition for a combinatorial batch code is where you have a set of m elements, those are the servers, and rather than having subgroups whose elements are items on the server, here we're going to have that each subset corresponds to an item, and in that subset is the list of servers on which that item is stored. And so for a dual definition here, we want to have a multifamily of subsets so that if you take any collection of L items, where L is at most the capacity, then you need to be able to, from those sets, find a system of distinct representatives, because that will tell you exactly which servers would be able to deliver those particular movies. So going back to, and so another way of identifying this is that really you're trying to come up with a matrix that codes this particular storage system so that any k columns has a k transversal. That's really what it boils down to. So in our particular example here, I have 5 different items, so associated to each of those items are these 5 subsets of servers. And if I wanted to, say, pick 3 items, I'll pick 2, 4, and 5 again. I'm trying to find a system of distinct representatives from the 2nd, the 4th, and the 5th set. And so I have a couple of options, but first I'll find a transversal in those columns, and that corresponds to this particular system of distinct representatives. So again, that SDR is going to correspond to exactly which server would be able to deliver each of your particular movies. Okay, so this is where we're going to tweak the definition a little bit. So erasure batch codes add a notion of redundancy. All right, suppose you have a situation where you might have one of your servers go down, and you still want to be able to have some amount of robustness in the system to be able to have the same delivery capacity that you had before. And so, for example, if I had one of these servers go down with this particular storage configuration, I'm not going to be able to download the Avengers movie. Okay, now it would be tragic. So we need to have another copy of it somewhere else. And actually, that can be said for just about every one of the movies up there. So if I...
Except the important one, right?
Except the important one. Very good. Well, I'm going to, just for kicks, I'm going to go ahead and add one copy of that as well. It turns out that you need to, in order for this particular configuration to have your desired capacity for deliverance. So that's what we're going to be looking at is, if you have this extra condition that you want to, if you were to take down one of the servers, still be able to deliver any 3 movies, or if the second server went down, still be able to have the same delivery, how many extra ones, how many extra copies of your movies would you need? And so this has been introduced recently and somewhat independently. One of 2B students Natalia Silverstein had looked at this in a very brief manner as well. But really, it's just a combinatorial batch code with this additional parameter R. And now what we're going to say is that an erasure combinatorial batch code with redundancy R is going to be a family of servers or subsets of our items, so that for any k items and for any m minus r servers, so R is the redundancy, that's also the failure rate, that's how many servers might be down at any given moment in time. You need to have that, you can find subsets of your up servers so that you can find every single movie in the union of those subsets. Again, I'm going to focus on t equal 1 just for simplicity, but also there has been some work done when t is not 1, and it leverages the fact that if you take one of the matrices identified with this and just take t copies of it and just sandwich them together, you can get some results on that, but I'm not going to talk about that. Okay, so there's also a dual definition. This one's a little bit more useful when looking at an example. If you look at the dual system of an erasure combinatorial batch code, again, we're going to have our sets being the items, the elements of which are the servers on which those items are stored, and we need to have that for every m minus r subset of servers. So if we were to, excuse me, have r of the servers go down, we have m minus r of the servers left up, we need to make sure that if we intersect the up servers with each of our items subsets, that we still can find a system of distinct representatives. Now, this is kind of a clunky definition. The more simple way to see this is that really, rather than just picking k columns and wanting to find a transversal size k, you're wanting to find a submatrix with k columns and m minus r rows, and you're trying to find a k transversal. Okay, so when it comes to trying to classify when something is a combinatorial batch code or not, often there's a nice Hall condition associated with it. And this, of course, comes up anytime you're doing something with systems of distinct representatives. The way that you would phrase this is the following. If you have a dual system for a combinatorial batch code, again, these are the sets associated with each item. So these are the columns of our arrangement. We just need to have that if we take any up to k columns and take their union, that we have at least that many elements in the union. That guarantees that we can find a selection of servers for which each of the movies can be delivered. Now, if you want to have redundancy with this, the condition gets a little bit more complicated, but it's not too bad. Now what we have to do is say that for any collection of up servers, we need to have that if we look at the subsets gotten by intersecting with the up servers, that we can still find a system of distinct representatives. And so the Hall condition then would say that we need for all sets of up servers that the union of any j items with the up servers is going to have at least j things in it. And that's still a little complicated because it involves needing to know something about which of the up servers are, but with a little bit of work, this particular condition is really just requiring that all of your columns, when you take their union, give you the redundancy plus the number of columns that you're unioning. So the normal Hall condition just says that if you have some number of sets and you want a system of distinct representatives, you union them and make sure you have that many elements in the union. Here, if you want the redundancy, then your condition just has that extra redundancy parameter R associated with it. Okay, so some necessary observations. In a combinatorial batch code, each column is going to have cardinality at least one, because everything needs to be available and on one server. However, if you have an erasure combinatorial batch code, each cardinality has to be at least R plus 1, because if R of the servers can go down, you need one of them to still be available. And similarly, you can get an upper bound if you have an optimal combinatorial batch code. You really don't need to have more than k ones in a given column. And for an optimal erasure combinatorial batch code, you need at most R plus k ones in a column. You don't need to have any more storage than essentially what the draw is that you want your particular capacity to be, along with having this added redundancy. Okay, so that then tells you that in an optimal arrangement, the weight of a combinatorial batch code is going to have to be between n and kn. Again, k is the capacity, n is your number of columns. And for an erasure combinatorial batch code, it's going to be r plus 1 times n and r plus k times n being your upper and lower bounds. Okay, so that being said, let me go over a couple of results that we found. We looked at Doug's paper and also a paper by Bustos and Tuza, where they found some optimal values for some different parameter ranges, and we were able to generalize some of them, and also we have got some other stuff at the end that I'll mention here in a bit. But the first one that I want to mention is that if you have a situation where the number of items is less than the number of columns, then the number of items you need to store on the server is just going to be the number of items. Here's an example. If you have this many items in this many servers, just use the first n servers and you'll be able to meet any demand that you like. For erasure batch codes, all you need to do is have r plus 1 copies of each movie on the servers as well. And the proof for this is a little less trivial, but you'd start with the same arrangement that you had before, and then you just have to add some additional copies in this circular-like manner. And this would be a configuration that would meet a demand, any demand really, where you've got a redundancy of size 2. So you can take down any 2 servers and still be able to meet any demand up to 4. Okay, if you want to be able to have maximum retrieval, so if you've got m servers, and each of them can serve 1 item, then that means you might be able to draw m items. Then the optimal solution is given by this particular way here. This is the picture for it. For your first m items, just have them appear on each of the m servers, and then just load your last 2 items on every server. And if you want to look at the erasure version of this, then what you're going to do is start with this configuration here, and then just pad all the ones in the first m columns. And in this particular example, if you take away any 2 rows, you're still going to be able to meet the demand of delivering any 4 items that you would like. Okay, now the rest of the results that are known in this area is gotten by first fixing your number of servers and what your capacity for deliverance is, and then letting n vary, the number of items. And so here is the spectrum of what n could be, and the number of items could be as low as 1, and it could go up indefinitely. And what's known for batch codes, well, we already saw earlier that if the number of items you have is up to the number of servers, then you just need to put a 1 in every column. If you have 1 more item than you have servers, that was also from Doug's paper, you just put 1 row in every column for the first m, and then just load the last column with k1s. When m is, when you have 2 more items than you have servers, I guess I was going to finish talking about what you did. If you have that n is arbitrarily large, when it's larger than some particular bound, you're also able to find an optimal configuration. If you have 2 more items than you have servers, jointly, oh golly, I gotta try and remember these names. Richard, it was Rualdi and Tiernan, Seth Myers, and myself. We were able to use some similar constructions involving transversal matrix in order to find the lower bound for that particular set of parameters. And then Bustos and Tuza also came up with a more elegant, I would argue, combinatorial construction for that bound. And also in that paper and in a couple other papers, they were able to push the bound on n lower, and they were able to, in one paper, get it down to m choose k minus 2, and then also later in that paper, they were able to push it a little bit further, but this particular bound is kind of complicated, and I didn't want to put it in here. So there's actually a large range where just combinatorial batch codes, the optimum value is not known. All right, so we already looked at this particular parameter range for erasure batch codes. That's where we just had to pad more 1s in the columns. Let me talk about this one for a minute, where you have that n is arbitrarily large. So in that paper by Patterson, Stinson, and Way, if n is larger than this particular value here, you can find an optimal solution. It's best seen by example. I'm not going to show why you can't do better in any of these, because that would be a little complicated. But the way that you construct this is you look at all of the k-1 subsets of servers, and you put k-1 copies of each of those columns in there, and then you pad the last number of rows with k-1s in them. If you want to do something similar for erasure combinatorial batch codes, really you just need to have more ones in place. So what we'll do is in each of our columns we will have r plus k-1 ones, and then we'll have r plus k-1s in each of the trailing columns. Let's see, what other range are we going to talk about? Let's talk about this range here when you have one more server. This one is somewhat of a sore spot. There's a nice way of computing it when you have combinatorial batch code. If you have one more item than you have servers, you just put ones on the diagonal and then put k-1s in the last column. However, there's not a nice analog for this for erasure combinatorial batch codes. I'll give you two examples of that. Here's an example where I have, if I have an erasure value of 1, then I'm going to have two ones in each of my first column, so I'll pad those in the way I did before. And rather than just, well, I'm sorry, and now I'd add a 1 here. That's the example I had before. That's right. So this right here actually gives me an upper bound on what this particular parameter could be. But actually, if you have that n is large enough, you can do better than having r plus k-1s in this last column. For example, if I take that n is 7, I'm sorry, n is 6 and n is 7, I have one more column here. In this case, I have, well, actually only 2 ones in that last column. And I'm still able to meet the demand. So there's some funniness that happens when you're kind of near the lower end that you don't get when you have that your number of items is relatively large. Okay, so that takes care of that case. The last case I want to talk about is this one here, and I'm going to go through it somewhat quickly because I've got 2 minutes left. So Bushtes and Tuza came up with the value of that particular optimum configuration. And really it turns out that underlying this, you need to find a packing design. And knowing the existence of a particular packing design allows you to construct this particular combinatorial batch code. And when you don't have any redundancy, that packing design is actually a design. It makes the inequalities very nice. But if you don't have a design, then when you look at erasure batch codes, you get a messier inequality that has a parameter in there that is dependent on the existence of a particular size packing design. And so we were able to classify it, but it wasn't quite as nice. Okay, I'm going to skip the directions for that. So we were able to generalize these particular parameter ranges. The other two ranges are kind of hard. This is what the lower bound is if you have 2 more items than you have servers, and it involves having a messy ceiling of a square root term. And the other range that was kind of towards the far end, they're known. It comes from just fixing what the values of k are, but it's just a giant mess. There are several cases to consider, and we didn't even look at it. So there may be some ECDC versions for this, but we don't know. And the last thing I want to mention is on the trivial lower bound. So every column in an ECBC has to have r plus 1 ones in it, because if r of the servers go down, you still have to have availability to download. So that was an interesting kind of side note from this, was that there was a time with graphs that we weren't expecting. And so I think with that, I will call it a day. Thank you. And you can ask me questions later, because I already ate to somebody's time.
Okay, I'm sorry, there's no time. The second speaker